Hello everyone, my name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. Okay, in last class we already discussed the uh, natural convection phenomena and forced convection phenomena. In this class we will see different numericals which are based upon the convection, either natural convection or forced convection. The numericals which are related to flow over a flat plate or circular plate. Okay. We'll see one by one. First numerical we'll see air at 20 degrees Celsius flow to say fast plate. Okay, so this is the plate, uh, rectangular plate. Okay. Flow is flowing like this one. U alpha is equal to 2.5 meter per second. Okay. The plate measures 600 into 300. So 600 is the lengthwise, 300 is the widthwise. It means 0.6 into 0.3 meters square area. So it is maintained at uniform temperature. So Ts temperature, Ts is equal to 95 degrees Celsius, and calculate the heat loss from the plate. It means you have to find out the P value. If air flows parallel to 600 mm, so air is flowing parallel to 600 mm. Just we have to consider the lengthways, 600 mm lengthways. Okay. So it means characteristic length you have to take to 600 mm. It means 0.6 meters. Okay. So if the air flows parallel to 600 mm side, how would this heat loss be affected? Okay. If the flow of air is made parallel to 300 mm. So here there are two conditions. One, the flow parallel to 600 mm. That is one condition. By that one, you have to find out the Q1 value with respect to 600 mm. Then the flow then the flow parallel to 300 mm. So that is the second condition. Flow in this direction, flow this direction. So this is the 600 with respect to, this is the 300 with respect to. So this one is the Q2, this one is the Q1. Okay. So then you have to find out the effect of these two. What is the percentage of heat loss between these two? Okay. So these are the given data. You can understand the what are the parameters have have been given. Okay. So first two, that is the air temperature has been given. Atmospheric temperature or dry air temperature is equal to 25 degrees Celsius. Okay. Then velocity is equal to 2.5 meter per second. Okay. Then Ts, solid surface temperature or plate surface temperature, is equal to 95 degrees Celsius. L is equal to 600 mm, nothing but 0.6 meters. Wide, W is equal to 300 mm, 0.3 meters. Okay. So first we have to find out the Q. If the air flows parallel to 600 mm, you can represent this is the Q1 otherwise. Okay. If the air flows parallel to 300 mm, okay, so then that is the Q2 you have to find out. Then find the percentage of heat loss between these two. Okay. So two conditions: heat loss with respect to 600 mm, heat loss with respect to 300 mm side. We'll see. First of all, we have to find out the T mean or bulk temperatures. So T mean or T mean is equal to Ts plus Tf by 2. Okay. So 95 plus 25 by 2. So 120 by 2, 60 degrees Celsius. Okay. So take properties of air. Take properties of air. So with respect to 60 degrees, by the help of the data book, you can refer this one, page number 34, according to Kodanraman data book. Okay. So these are the properties. Prandtl value of the dry air, kinematic viscosity of the dry air, thermal conductivity of the dry air. So these are the required data taken from the data book with respect to 60 degrees of dry air. Okay. Then you have to find out the Reynolds value, because the velocity has been given means you can understand this is the forced convection. Okay. So if the velocity is not given, you can understand that is the natural convection. Small point. Okay, Re is equal to Reynolds UL by mu. Okay. So here we are taking the full length. Full length, it means length is 600 mm. Then U velocity, so that is 25. Okay, not 2.5, 25. 25 meter per second into 0.6, that is the length along 600 mm by kinematic viscosity value, that is 1897 into 10 to the power of minus 6, 18.97 into 10 to the power of minus 6. Okay, if you solve this one, then you can find Reynolds value. Here Reynolds value what we got, so that is 7.91 into 10 to the power of 4. So this value, Reynolds value, is less than 5 into 10 to the power of 5. If it is less than, you can understand this flow is the laminar. So this is a laminar. So based upon the flow and the lengthwise. So here we are taking the full length. Then you can take the Nusselt formula. Nusselt for full length, average laminar flow is equal to 0.664 into Re to the power of 0.5, Prandtl to the power of 0.33. Okay, it means 1 by 3. So if you substitute the value of Ra and Prandtl values here, then you can find the Nusselt formula. Okay, Nusselt formula. Then by using this Nusselt formula, you can find out the H value, because you know that Nusselt is equal to HL by K. By using that formula, you can find out the H value. If you know the H value, you can find out the Q1. Q1 with respect to 600 mm is equal to HA into temperature difference Ts minus Tf. Okay, so this is the value. Uh, Next in second case, with respect to 300 mm, that L is equal to 0.3. Okay, parallel to 300 mm. Here also same process. You have to find out the Reynolds value. UL, L is equal to 0.3. Okay, this is the kinematic viscosity. U is the velocity, the given velocity. If you substitute all the values, you will get. So the value of Reynolds value, this is the 3.95 into 10 to the power of 4. So this one also less than 5 into 10 to the power of 5 means this is the laminar flow. Okay. So flow is laminar flow and L is full length. Then you can say take the formula, same formula, 0.664 into Re to the power of 1 by 2, Prandtl to the power of 1 by 3. If you substitute the Re, Reynolds value of this one, Prandtl is the we got already from the data book. If you substitute the values, you will get to Nusselt value. Then you have to find out the H bar. So Nusselt is equal to HL by K. By using this one, you can find out the H bar. Okay, then you can find out the Q2. Okay. So Q2 is equal to HA into delta T. H into A is the area into length into width, same. This is the Q2 value. So then heat loss is equal to Q2 is the bigger one, Q2 minus Q1 by Q1 into 100. Okay, so this is the value we got. So percentage of loss is equal to 41%, 41.32. Okay, so with respect to 600, with respect to 300, we will see one more numerical. Air at a atmospheric pressure, uh, so that is the 90 degrees Celsius flows with a velocity. Here also velocity given means we can understand this is the forced convection. Tube diameter also given, diameter of the tube. Uh, Fluid is equal to air. The tube is maintained up to Ts is equal to 650. And to calculate the rate of heat transfer per meter length, you have to find out Q by L and use the following relation. So, the first of all, T mean you have to find out. T mean is equal to Ts plus Tf by 2. So, 90 plus, mm, so tube temperature is equal to 650, then 370. With respect to 370 degrees Celsius, you have to take the properties of the air. So, thermal conductivity of that air is equal to 49.13 into 10 to the power of minus 3. Okay. Kinematic viscosity is equal to 57.5 into 10 to the power of minus 6. So this is the values. By using these values, you can find out the rate of heat transfer. First of all, you know that you have to find out the Reynolds value, UD, because L is equal to diameter, because it is the circular pipe, UD by mu. U velocity is given 8, diameter also given 0.025, and kinematic viscosity 57.5 into 10 to the power minus 6. So then Reynolds value is equal to 348 degrees Celsius. So then, okay, so TWTS. Then you can take this formula, because this is a 342 less than 300 3200. So this is the laminar flow. So laminar flow, this one is the formula 0.66 into Re to the power of 0.4 by 5, otherwise into Prandtl to the power of 4. So just like this is the formulas you can take. Okay. If you substitute that values, then you can find out the H values. If you know the H values, then automatically find out the rate of heat transfer. Q is equal to HA into temperature difference. So by using this one, you can find out 295 kilojoule per kg Kelvin. So we'll see. Uh, this is the one more numerical. Just to, I would like to give outlines of this one. Then you can solve this. Estimate the heat transfer from 40 watts in condensate to bulb. So that is the temperature 125 degrees Celsius to 25 degrees Celsius in quiescent air. So approximate the bulb as 50 diameter sphere. So what percentage power loss by free convection? The appropriate correlation also given, that is the formula Nusselt is equal to 0.6 into GRPR whole to the power of 0.25. You know the temperatures has been given, means we have to find out the T mean 125 plus 25. So that is the 75. At 75 degrees Celsius, you have to take the properties of the air. So these are the properties: kinematic viscosity, thermal conductivity, and Prandtl values. Then beta is equal to 1 by T mean. Okay, T mean plus 273. So you can find out the beta value. So if you know all these values, then you have to find out the gross up number. So GR is equal to that formula G beta delta T LCQ by kinematic viscosity square. If you substitute G, you know that beta also, you know that temperature difference, you also know that LC is the length of the pipe, characteristic length. You already you can take that one. Next to kinematic viscosity square. If you substitute all the values, you will get the gross up number. Gross up number is equal to 8.0 into 10 to the power of 5. Okay. So by using this correlation formula, then by using the then you have to find out the GRPR. By using the product of GRPR, we can take the Nusselt formula. Okay, so this is the Nusselt formula. This one already given in the numerical. Then you can substitute the values 0.6 into, this is the gross up number values. This one is the Prandtl values. So then by using Nusselt formula, you can find out the H value, because Nusselt is equal to HL by K. Okay, so if you know the H value, you can find out the Q value. Q is equal to HA into delta T. Okay. So So if you substitute the H value and A is equal to 5 for D square or pi R square into temperature difference 125 minus 25, then you will get the heat transfer, rate of heat transfer. So that is a 7.71 watts. Okay. So this is the percentage of heat loss also you can find out. So 7.71 is given. So already used that one is the 40. By using this one, you can find out percentage of heat loss. So in this way, just you can solve different numericals. These are the test books to further reference I have given. You can refer these test books. So thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.